Hello and welcome. This is Jason Kendall to one of my introductory astronomy lectures, and this time we're talking again about the nature of light. Light is that thing that allows us to see things from here to there to here. We don't emit light out of our eyes, unlike certain kind of superheroes who beams of light come out of their eyes. No, light, it comes to us from sources. Those sources might be hot objects that are so hot that they glow, or they're so hot that the atoms in them emit light as they jump between orbits in their atomic shells. There's lots of ways for light to be emitted, but let's just see what light is as a thing. And as we've always seen from like the album cover of Pink Floyd, and like we're looking at here, when light passes from one medium to another, it changes direction, and depending on the medium, it has a frequency dependence for the speed of light inside that new medium. But the speed of light that we're going to care about comes up really shortly. In any event, what is light? Well, light is electromagnetic radiation. And electromagnetic radiation is a way of saying that energy is being transported through space without there being a physical connection between the two things. There's no actual physical link. So electromagnetic radiation is a transfer of energy. The other two examples where energy gets transferred are conduction, where you heat something up and the vibrations of the molecules and atoms inside of that object that you're heating up, they vibrate against each other, and eventually all the atoms move very fast. And if you happen to be heating up a skillet or a pan on sort of an open fire or a heating element, then eventually the handle gets hot too. So that's called conduction. Conduction is the vibration and the collisions of atoms inside a solid object, or any object where the atoms and molecules inside it are close enough together that their vibrations can impact each other. So that's physical contact. Another way that physical contact can occur is through convection. Convection is where you take a hot body of some sort, a hot bubble of gas or liquid or what have you, or even a hot solid, and you move it from here to there by some physical process. The heat then is transferred, the energy is transferred because now you've got something with a greater amount of energy, and you take it from here and you put it there, presumably to a place of lower energy or lower heat. Or you could place it to a place for higher energy, but then it would gain more energy. So that's not really the flow that we think of in terms of convection. So a good example is a boiling pot. You heat the pot, the bottom of the pot gets hot, makes a bubble of hot water. That water then rises in the pot, releases it as steam or heat into the surrounding to the kitchen, and then that cooler liquid then sinks back down. It makes a roiling pot. So there's actually a flow of water inside the pot as it goes. So that's convection. It also happens with air. That's how we get storms, because there's convective cells in storms, and so we've seen that happen all over the Earth with the creation of hurricanes and so forth. But with electromagnetic radiation, radiative transfer of energy does not require the physical contact. Convection means you transfer objects that are physically moving through each other. This bubble that's hot moves through a region until it gets to a region where it's cool. Conduction is where electrons bounce against other electrons right next to each other. But if it's radiative transfer, electrons and protons don't go, oh, I'm going to touch you and move along. No, it's light. Light actually transfers its energy from here to there. So there is no physical contact that the photon does. It's just a thing that it transmits energy. And so light is something, but let's get to it in just a little bit. That's a very complex question, but light's everywhere. The reason you can see me now is because light's bouncing off of me, getting recorded by the camera. The camera then holds it as an electromagnetic impulse, and then I transfer it to the computer. After I transfer it to the computer, I play around with it on the computer, manipulating the electric and magnetic fields on the computer. And then I upload it using electromagnetic fields to YouTube. And after I transfer it to YouTube, you then turn on your computer and using more electromagnetic energy. That creates light that comes out of the screen, which you then see. Interesting. But what is this light thing? This thing that is transmitting energy from me through the magic of YouTube to you. Anyway, there are characteristics to light that we should discuss before we say what light is, because we can't discuss what it is without discussing its characteristics, and one of them is wave motion. So light has a wave property, meaning that there's wavelength to light. And light's wavelength is a very important thing. So what do we mean by wavelength? Wavelengths, if we take some sort of medium, and we have a regular disturbance in it, we get waves that go up and down, like water waves. Water waves are a perfect example of wave activity. In water waves, we see the distance between the crests in water waves, and those distances are the wavelength. So the wavelength is the distance between crests or troughs in a wave as it traverses. And so it's a cyclic pattern. It's just not one wave. There's many waves in a train of waves. And the train of waves has a speed with which they move through the medium. Say the water waves move at whatever speed they do through water. And that speed is important because the speed of the wave is equal to the frequency, or how many waves go by you per second, times the wavelength of it. So if you have a high frequency, then if you have wavelengths of the same type, same length, and one of them is high frequency, then of course the waves are moving faster by you. If the same frequency is occurring, but one of the wavelengths is much shorter than the other, then the one that's long, then the smaller wavelength thing at the same frequency has a much slower wave speed. Now we're going to see something interesting about the nature of what we call the period of the wave, is what the time is between individual cycles. All right, so in terms of the speed of light is a constant in vacuum. It only has one speed. There is no other speed to light. It either is not existing, meaning there is no light, or it's going this speed, which is very interesting. There's no acceleration or deceleration to light. Light just simply goes at this speed, the speed of light, which is just shy of 300,000 kilometers per second, or just shy of 186,000 miles per second. But specifically, it's 299,792.458 kilometers per second, which is a very fast speed. That means it gets to the moon and back in 2 seconds. That's why those pings in the Apollo missions, where they have that little ping sound, because it's rude to talk over people, and you actually want to know. So you send the ping to say, I'm done with transmission, because it takes a second for the light transmission to get from the Earth to the moon. And that's why they had the ping sound at the end of the Apollo mission transmissions when they were talking back and forth between the moon and Houston. So what does that mean? So if you have the speed of light being a constant, then the product of the frequency times the wavelength gives you the speed. All right, so if the speed's always the same, then if you have a long wavelength, you have a short frequency. And if you have a short wavelength, you have a high frequency. And so they're inversely related. Because the speed of light is a constant. So once again, if you have a very small wavelength, lambda is typically what we use for wavelength, then you must have a very, very, very high frequency in order to maintain that speed. And if you have a very low frequency, then you must have a very long wavelength, and those are radio waves. The other one are gamma rays. So light goes in all sorts of flavors, but it all travels at exactly the same speed. All right, so how do we know what the speed of light is? Well, the speed of light, as we discussed in a previous lecture, was first investigated, or at least investigated in many ways, but Ole Romer looked about it by looking at the transits of Io across Jupiter over a long period of time, over many months, and actually noticing that the times that it was expected to be were wrong. But another more direct way to do it is with Fizeau, who actually used mirrors on tops of mountains and actually bounced light all the way across and through a rotating toothed wheel. And the toothed wheel spun and spun and spun. And as the light passed through the wheel and bounced off the mirror and came back, it had to make that trip while the wheel was rotating, and the light had to come back through the same tooth it left, or else it would be blurred. So Fizeau made it a pulsing beam, and that pulsed beam had to have the same speed as the light going through it, or else it would get blocked. And so you either get blocked light, or you would get, or you'd let it through. And how you determine the speed of light was how fast was the gear, how fast is the rotary wheel turning, what's the length of space between the teeth. And so you could say, well, how long did it take for light to go all the way down and back, such that you don't get a distortion, you don't get a blurred view. And that's one way of determining it, how fast the wheel's rotating and the size that it's rotating through. In any event, the wave nature of light was determined because you can actually say, well, what are some features of wave light? Is that light diffracts around boundaries, just like water waves do. So when water hits a boundary like a jetty, it curves around that jetty. It doesn't actually stop. It doesn't go around it. When it goes past it, it doesn't not go around it. You don't see waves not propagating. Waves have a way of actually spreading out, and so they don't stay trained on one place. They just spread out until they thin out across their breadth, if it's a water wave. But in terms of like a jetty going around, as soon as it passes the jetty, it starts to spread back out around the jetty. In any event, you could have interferences of waves, where waves can constructively interfere and destructively interfere. And if the waves constructively interfere, that means the two waves merge together. And if their peaks match at a given place in space, then they add together. If their peaks are if one wave's peak matches another, the same wavelength's wave's trough, then they cancel out. So you can either have what's called interfering constructively, meaning they add together, or they can destructively interfere and subtract from each other. Basically, the waves superimpose and add to each other, and the trough acts like a negative number and the peak acts like a positive number. So if it's a wave height of 2 and the other wave height is 2, and they happen to be at the same place, at the peaks are at the same place at the same time, then the wave height is not 4. But if the wave trough is at the same place as a peak, then the wave height is 0 and it's flat. So you can have waves passing through each other and not make a noise. It's kind of a weird thought, but it can happen. So constructive and destructive wave interference can be seen pretty easily. If you look at it, drop 2 stones in a puddle of water, you can see 2 outbound ripples. It helps to have some nice sunshine, so you can actually point out the troughs in the water and the peaks in the water. And it's pretty easy to see as you try it out at home, because what the heck, everybody's got puddles of water around them, and maybe something deep, and you can see the reflection of water on it and see the constructive and destructive interference. Another thing to look at is back in 1901 or so, or the early part of the 20th century, Young did what is famous Double-Slit experiment, where he put a slit inside a barrier to make an image of a slit as a single source, and then allowed that image of that slit then to spread out, because light spreads out from a source diffractively, to impact on 2 other slits. And those 2 other slits then, they each act as sources, but those sources, then what we see on the far side is a constructive and destructive interference pattern on the far side of it. So you have a source, a continuous source going through a slit. That slit then goes through a double slit, and that double slit then makes constructive and destructive interference patterns, which can only occur if light has wave properties. So Young's experiment actually proved that light actually did have wave properties. So what are some effects of wave properties? Well, let's say you were moving towards or away from something. We've always heard of the nature of wave properties. So let's say you're going to see a Doppler effect, and Doppler effects occur because, let's say you see a car driving towards you and it's honking its horn. The pitch will be slightly increased as the car is driving towards you, and if it's driving away from you, the pitch will be slightly decreased. And I had the benefit of going to the Indy 500 a long time ago with my good friend and best man for my wedding, Ralph Hafner. And Ralph got tickets for us to go see it, and you could really hear the effect of the Doppler effect as the cars flew by you. Okay, so just to say it, when cars in the Indy 500 are driving, they're these little things, and they're extremely loud. They go, oh, right? They're driving like that. They're driving really fast, oh, really fast. Now that sound, oh, is what you hear if you're inside the car. Now, what do you hear when you're seeing them go by on the track? What you hear is, oh, that's what you hear. Now, inside the car, it's oh, because that's the sound of the engine. They're really whiny. But outside, you hear oh as it approaches you, and then oh as it goes by you. And the pitch changes. So the wavelength of the sound changes to the observer. So I'm the observer sitting on the stands in the 4th row above the finish line going, yay, there's the cars. And I hear this sound. And everybody who's ever watched these kind of things has seen and heard this sound. It's a really cool sound. In any event, that's a Doppler effect. which is the change in wavelength or frequency as a result of a movement of the source towards you or away from you. So the Doppler effect is just that. You have the true wavelength, which is an oh inside the car, the sound of the engine. But then there is the perceived wavelength or the apparent wavelength, which depends on the relative motion of the source. So the faster something goes by you or towards you or away from you, the greater the Doppler effect is. So that's all dependent upon both the speed with which it's moving and the speed with which the wave travels, the sound wave. All right, so for light, we have a slightly different thing, but it works the same way because light has a wavelength. So if it has a wavelength, then we can see if there's a Doppler shift, and there is. So light has a wavelength, and there's a certain wavelength at which the light is emitted, and there's a certain wavelength at which the light is received. So if I were to actually take a red light, maybe it's 6,500 nanometers in wavelength. Maybe that's the wavelength I'm looking at. And that wavelength source of light, which by the way would be a cloud of hydrogen gas, if that wavelength of light is traveling towards me, or actually, let's make it go away. If it's going away from me at, say, 90% the speed of light, or maybe 80%, just to keep it easy. If we said if the light was going away from us at 80% the speed of light, then the total speed, then the wavelength change would actually change the wavelength to almost twice its wavelength, almost twice. So it would be well into the infrared, roughly about 1,200 nanometers. 1,200 nanometers as opposed to about 600 nanometers. So it'd be well into the infrared, and you wouldn't be able to see it. So if something's emitting, if it's a hydrogen class gas and it's rushing away from you, whatever reasons, hot hydrogen rushing away from you at 80% the speed of light, normally if it were still, you could see it. But if it's rushing away from you that fast, then the light gets redshifted down to the infrared, and you have to use infrared to see it. That will be important when we talk about the Big Bang. But in any event, Doppler shift is important in light because if the source is moving, then there is a Doppler shift. And that occurs in every direction. You can have a slightly changed version from it, away from it. If you're looking at it from the side, there's a part, the part of the motion that's towards you changes it. So effectively the light bunches up in the direction of it that it's going, changing the frequency to a higher frequency, and gets stretched out away from the source as if for things behind it. In any event, for wavelengths of light, like it shifts, but the important thing about the Doppler shift with respect to, say, let's say that cloud of hydrogen gas I was talking about, is that all the wavelengths get shifted by the exact same proportion. So the spacing between the wavelengths, that is not dependent on the speed. So the pattern stays the same. It just gets shifted by the same amount, either blue shifted, meaning if it's going to a shorter wavelength, or red shifted, it's going to a longer wavelength. And if something's receding at, like, say, 1% the speed of light, if it's receding, then it'll be slightly red shifted. If it's riding towards you, approaching at a much faster rate, maybe 2% the speed of light, then it'll be much greater. But on every case, all of the emission is simply just shifted by that same amount to the left or to the right, by the same amount. And they don't get stretched out or pulled out in any direction. All right, where can we measure this? I just said gas cloud, hydrogen, rushing away. Well, what if it's rotating? Let's say you've got some rotating, glowing object. If it's rotating and glowing, then the side that's rotating, maybe a big, hot, glowing ball. That's kind of weird. Big, hot, glowing ball, rotating really fast. When it's rotating really fast, the side that's approaching you would be blue shifted, and the side that's retreating away from you would be red shifted. And so you can have a Doppler shift on a big, hot, rotating ball of gas. Maybe a super fast rotating star or something, or even a moderately rotating star can show a Doppler shift. In fact, the sun shows a slight Doppler shift at visible wavelengths, but you got to be really sensitive to see it. If you have two stars that are orbiting each other and they're part of a binary system, then those two stars then also show this Doppler shift because, hey, maybe one of them is approaching and one of them is receding. So all of the spectral features of the star that's approaching you get shifted to the blue, and all the spectral features of the star that's receding away from you get shifted to the red, and then they swap back and forth as one's receding and one's retreating, and the other's retreating and the other's receding. So That's another thing. Look for binaries that do this. And finally, as the Earth goes around the sun, it's even very interesting, is that there's a slight Doppler shift as the Earth goes around the sun with respect to all of the stars in the sky. So that's a very small amount. And that has to be taken into account if you're being very sensitive with respect to spectroscopy. So the Earth's motion around the sun can cause a Doppler shift in stars. All right, so is it real? What's real speed? So what's the real speed? I mean, I know I'm going fast with respect to you, but what's the real speed? What's my real speed? Well, there is no real speed. There's only relative speed. The Doppler shift only cares about relative speed. There is no absolute speed, meaning, okay, if I could find my reference frame such that I'm going the absolute speed, then everything is going to be fine. That sounds like something you might hear about in a comic book, maybe. It's like, oh, I'm going the absolute speed. Kind of a Flash thing or something. So you're going at absolute speed, but there is no absolute speed. That's an odd thought. But there is one absolute speed, the speed of light, but that's the speed that the light's going, and it only goes that speed. So that's kind of weird to think. So there's really no such thing as a true speed, meaning the speed with respect to the space and time. Because all space and time is relative. So you have to measure Doppler shift with respect to your speed, with respect to the source or the observer. And if one's moving, the other one could be moving in exactly the same way. In the same sense that the Doppler shift would occur if in the Indy 500, everybody in the Indy 500 stands were simply moving by the car and the car was standing still. The Doppler shift would still occur for the people in the stands. That would be very jarring to realize that the car is standing still and the entire city of Indianapolis is moving, but it would have the same effect in terms of the Doppler effect. All right, so what do we mean by the wave nature of light and what do we get out of it? And one of the nice things that we see is that you get pretty rainbows. And pretty rainbows are part of the wave nature of light because as light enters a prism, the speed of light changes, and in a prism, in glass, the speed of light is a function of wavelength and frequency. So the blue light is bent more than the red light, and so there is a frequency dependence, and so the light spreads out as it passes from air into glass, and then from glass back into air. The change in medium actually, because it goes through the glass, it actually gets spread out by the glass. Anyway, our more important thing is the pretty rainbows that are caused by water droplets in the air or by pretty prisms hanging in your window. Is that the visible spectrum, that which we can see is called the visible electromagnetic spectrum. And the visible electromagnetic spectrum is roughly between about 4,000 angstroms and about 7,000 angstroms, or 400 nanometers to 700 nanometers. And it spans from the violet all the way through the deep, deep red. And if it's shorter wavelength than violet, we call it ultraviolet. And if it's longer wavelength than red, we call it infrared. And their frequencies are very high. They're on the order of 10 to the 14th cycles per second. But the wavelengths, let's look at the wavelengths for just a second. 400 to 700 nanometers. We already know that there's wave properties about light, and since light has wave properties, it does diffraction. So why don't we see diffraction everywhere? Why isn't everything fuzzy? Because waves of light which should make things fuzzy. I mean, we have eyes, and as light enters our eyes, it's an aperture, and the aperture then means that inside your eye, the light must spread out. So why isn't everything all fuzzy? Well, because the wavelength is very small with respect to the aperture of your iris of your eyeball. So your iris of your eyeball is a couple of millimeters, right? It's a few millimeters. That's really big compared to nanometers. So there's an order of tens of thousands of them. So if you're looking at like 700 nanometers or 500 nanometers, let's keep it simple. And that's many thousands of times smaller than the size of your iris. And so waves don't really notice the diffraction. So the diffraction effects are not very noticeable. However, if you wish to see them, take this little experiment. Take two of your fingers together like this and just barely close them. So there's just a tiny bit of light between them. Hold them close together so there's just a little bit of light, and bring it close to your eye and look at some bright light source. And you'll see in between your fingers dark and light bands. That's some diffraction patterns happening because of the diffraction around the edges of your fingers. So it's really kind of pretty. You can see that with just your fingers. All right. So a fun thing is that light comes in frequencies and wavelengths, and packets of light called photons do that, and that's what we call light. Well, here's the funny thing. Because individual packets of light called photons have individual frequencies, then there's really no such thing as color. Color is a construct. It's a biological construct in your brain. What does that mean? Well, it means that there are cells in your eye which are receptive to certain ranges of color. And if they're receptive to, say, maybe 50 nanometers from, say, 500 nanometers to 550 nanometers, maybe that's the sensitivity of that cell in your retina, in your eye. And the rods and cones, the cones in your eye are receptive to many wavelength bands. And so if you can see many, many colors, and you are gifted to see many colors, then you have lots of different sensors, and they're very fine, and they can see lots of different things, and you have lots of ways that you get that very narrow bands of frequencies to which these cells are sensitive. So your brain then takes this information as the cells are fired off by the light, and they say, oh, I can see this. I get a photon, I get a photon, I get a photon. But then your brain then says, ooh, that's the cell that makes purple. That's the cell that makes green. That's the cell that makes red. And where'd you get those words from? Those words came from what everybody called that thing that we call red. And that redness is what we culturally call red. Isn't that interesting? So color is in your brain. You construct it because you add photons inside of a filtered frequency receptor. And that receptor is called a cell. And the cells can see lots of different bands. And it's the difference in brightness between your yellow receptors and your blue receptors, or your blue receptors and your red receptors, that tells you what the color is. If your red receptors are really firing off and your blue receptors are not, then you'll call it red. If your green receptors are firing off and neither the other two are, then you'll call it green. That's how color works, and we call that thing green. Now, people who are colorblind, their blue receptors and green receptors are fired equally, so you can't tell the difference. And that's kind of a sad thing for them, because they go, what the heck is that? I don't see green, I don't see blue. I just see kind of a gray. And that's what people who have color blindness. They can't tell the difference between the colors. All right, so that's pretty good. We'll see you next time.